here's what to expect in this session. We're going to talk about principle-based entity resolution and how features are examined in the ER process to determine changes to entities and relationships. We're also going to review the ER process that we started to talk about yesterday, and then we're going to get into data source selection, how to select data sources and features for entity resolution. So at this point, I'm going to turn most of the session over to Mr. Butcher, and he's going to walk us back through the entity resolution process, so the life of a record as it becomes a part of an entity or changes an entity. And we're going to spend specific focus on what happens when principles are applied in stage 3, where the blue box is. So at this point, Jeff, I'm going to turn this over to you. There's a link to the entity resolution process white paper in your study packet. Please go ahead and open that now. We'll give you a minute or two to get that open in a separate tab on your desktop. We are going to refer to this paper quite a bit in today's session. So please just take a couple minutes and get that open.
So I'm just going to start with number 1 there, entity resolution overview. And the first step of entity resolution is obviously a record is presented for resolution. And so step A is receive the record. We store the record as we got it. That means the JSON and everything. One of the things about Senzing is we maintain full attribution. So we keep, what that means is we keep every version of the record I'm sorry, not every version. We keep every record that we receive. So, you know, when you look at survivorship, some systems, you know, only keep the best name, the best address. We keep everything. So that's the record library that you see. It's a table you could query. It's a table you could export. Every record presented to us. On those records are going to be the attributes, you know, name first, name last, adder line 1, all of that stuff. Those are, you know, name and addresses are features. They're examples of features. And we have standardization routines for every feature. A name goes through a name standardization, an address goes through an address standardization, social security number goes through a social security number standardization. And that is, you know, like an address is composed of elements, adder line 1, adder city, adder state. So we standardize those as much as possible. And that goes into our feature library. I was saying yesterday, the name Jeff Butcher is, you know, has one and only one record in the feature library. And we can, that makes it easier for us to count how many records came in with that feature, with the feature, the name Jeff Butcher. It's just an integer feature library. Jeff Butcher is 1,000, let's say. Now, after we compute features, after we standardize the features, we compute new features. And I refer to these as expressions. So expressions help us find records in a billion record database. So the name Joe Smith might have 1,000 entities using the name Joe Smith. There might be 50,000 people born on a certain date, but how many Joe Smiths were born on a certain date? That's, you know, a much smaller number. So maybe there were 20 that were born, you know, December 1st, 2001, let's say. That's a expression of the record. And it's a new feature that we add, and it helps us find candidates. So once we get that all ready to go, then we go on to step 2, where we look through all of the rest of the records and we try to find candidates. And, you know, we might find a candidate on name, like the exact name. We might find a candidate on address. We might find a candidate on one of our expressions. But in order to keep the system fast, you can't always, you know, return everybody that was born on a certain date, right? If there are 10,000 people born on that date, we're not going to return all those. So that step A, where it says determine candidate features, we're looking at the counts. How many people are using the name? How many people are using the address? And that's where the expressions come in, because there might be too many people with the name, too many people with the address. So it's the name and date of birth that gets somebody on the candidate list. Once we figure out what are good candidate builders out of all the features of the incoming record, then we go to the database and we select them all. That is the first part of step 2, select candidates. Now, if we, now we're on to step 3, and we have to compare all the features, because we might find, if we're searching for Joe Smith at 111 First Street, we might find 20 Joe Smiths, we might find 30 111 First Streets, and there's some overlap between the two, I'm sure. So what we have to do is score all the records. And that's our fuzziest logic, where we use global name recognition to compare the names. Let's say the incoming record, is a J Smith that lives at 111 First Street. So we find 10 candidates that live at 111 First Street. There's a J Smith, there's a Joe Smith, there's a Mary Smith, and there's a Bobby Smith, not 10-3. So then we compare all of those names, and the highest scoring name of all the people with that address is the Joe Smith to the J Smith. The Mary Smith isn't close, the Bobby Smith isn't close, but the Joe Smith is close to the incoming J Smith at 111 First Street. And once we have all of those scores, that's where we go apply our principles. And we're going to get into principles quite a bit on the next slide. But principles are a series of, I'm going to call them rules, but we refer to them as principles. But one of the first rules is, if the name and the address and the date of birth and the social security number, like if they have everything very good, that's going to be a match. So the Joe Smith at 111 First Street, that matches the J Smith. It's a pretty high name match. So that might hit a resolve rule on name and address. Then you get we have other candidates on the list though. So we have the Mary Smith, and the Mary Smith hits a principle that says they're only sharing the address. So what we find out here is who is who resolved and who only related. And then we're going to go on to step C of the third, part C of the third step, which is, did we learn something new? Now, if in that example where we have the Joe Smith coming in, let's say there's a phone number on the J Smith record that came in, and the entity that we're going to resolve it to doesn't have that phone number. Maybe they have a different one. Maybe they didn't have one at all. So, but we've learned something new about an entity that we have in our database. Whenever we learn something new, we go back up to step 2, and we determine if we can find more candidates. So there might have been let's say there's a Joe Smith record with that phone number and a Joe Smith record with that address. Those are 2 different entities. There wasn't enough to match them in the past. If the incoming record brings in a Joe Smith with the same address and the same phone number, once we learn the new phone number, we then go back up and see if we can pull anybody else into that entity. And that's where we snap all 3 of those records together. That's that real-time learning loop. There's another potential thing that happens in that real-time learning loop. We may find that we've introduced a discrepancy. Let's say instead of learning a new date of birth or a new phone number, we learn a new date of birth, same name, same address, but the date of birth is different than our entity. It would resolve, except there's a different date of birth. Now we're going to go into that step C, but in this instance, we're looking to break the record back apart. We found we found a match, but it introduces a discrepancy. Maybe we've made a mistake and there's like a Joe Jr. and a Joe Sr. So that's where we go back and do unresolved as well. In yesterday's sessions, one of the questions that came up is, man, if you do that a lot, you're going to get, it's going to be slower. So maybe the more data you have, the slower it's going to be. And I would just tell you on that issue, we only go into unresolved when we learn something new. Or I'm sorry, we only go into re-resolve when we learn something new. We only go into unresolved when we introduce a discrepancy, or when a discrepancy is introduced. So we're very careful about how we do that to keep the system fast. Now, we may go through an entity learning new things one time or two times or 20 times. But we do it until we've introduced nothing new into our entity map, as it were. That's when we go to step 4 and update the database. And what we update the database with is we have the Joe Smith, or the incoming J Smith record. He resolves to our Joe Smith entity. He's related to a Mary Smith on address. He's related to Bobby Smith on address. That's what we do when we update the database. And on step number 4 on A, that's the resolved entity graph. Then if requested, we respond with outcomes. And what that means is, record, or the J Smith record came in, what did you do with it? Well, we assigned it to entity number 1000. That's what we did with it. If we did do some moving around of other entities, like we pulled in 2 Joe Smiths that were previously not resolved together, then responding with outcome is going to tell you we assigned the incoming record 1001, but we also changed entity number 999 and 998. So you get a complete a message with how the entity graph was updated. And then that completes the process, and we go on to the next record. At this point, I'm going to ask if you all have any questions about this. Well, all right. Let's move on to the next slide. What are principles, and what is this thing called behavior-based entity resolution?
And the link to that paper is in our chat. So if you don't already have it open, please go ahead and open it up. What you're seeing on the screen now is just a snippet from that paper.
Right. So now, principle-based entity resolution, I use the term rules, but the rules are based on principles. That's why we call them principles. And if you're looking at that white paper, if you tell your child to quit throwing rocks at cars, that's a rule. And the next day you find them throwing baseballs at SUVs, and you have to tell them not to do that too, which would be a different rule. A few days later, you're telling them not to throw golf balls at trucks, fire engines, and ambulances, more and more rules. So instead of all those rules, why not one simple principle? Don't throw things at other people's stuff. And that, what we've done with our principles is we've come up with a similar philosophy for features, like how does a name behave? What are the principles? How do we group names together? How do we group, dates of things like dates of birth together? How do we group things like addresses and phones and socials together? And we came up with 3 questions that you could ask about any feature. And the first one is frequency. How many people should have the value? So an identifier is going to be a frequency 1. Only one entity should have it. This is usually like an ID number or an account number or an email. Or the answer to frequency could be a frequency few. Only a few people should have the value, or the next response to the frequency question could be only a few people should have it. And that's something like an address or a home phone. And I refer to these as contact methods, are usually frequency few. If you try to contact somebody, you might get them, you might get one of their family members, somebody in their household, somebody might answer their phone. That's a frequency few. And then there's just many. And that's sort of the default for everything else. Many entities can have this like a date of birth. So even though, date of birth is a very powerful feature to use for entity resolution, but many people could have it. So the frequency question is, you know, it's not as valuable from a frequency standpoint as, say, an account number or a social security number. And then we have the level of very many. Very many is, you know, something like gender, and that's it's just such a low domain. There's only 2 genders. It's not very discriminating. Well, there's more than 2 genders, but it's not a very discriminating feature. Citizenship and nationality kind of fall into that bucket as well. Is not as discriminating as like a date of birth. So there's one, few, many, or very many. Our internal keys all have a frequency of none. We don't use them for entity resolution. And name is a very special frequency. And part of the matching of names and how good it is part of the GNR, global name recognition technology.
Mr. Butcher, question from the chat.
Yeah.
Regarding email being designated in F1, we find some couples, especially older ones, share emails. How is that handled?
You know, I knew I was going to get this question. So our current setting for emails is frequency 1, but in past iterations, it has been a frequency few. And the default behavior that we settled on that works for most data sets is a frequency 1. However, if you feel in your data set has, you know, a bunch of shared email addresses, then you can certainly change it to a frequency few. But that's all you'd have to do. And then it would behave more like a name and an address match versus a name and a social security number match, or a name and an account number match. One more point to that question. Now, I recall we were doing a project in India one time, and they definitely were saying, hey, that email should, in India, everybody shares, the whole family shares an email address, right? So it's definitely a frequency few there. So there's nothing to prevent you from having a regular email that's a frequency 1, and say a shared email that's a frequency few. And so if one of your data sources, you know, has it as, you know, a more shared thing, then you can certainly map it 2 different ways. And I'll leave it at that for the.
Hey, Mr. Butcher, if you pop open the chat, you'll see some discussion going on about emails may not be a frequency 1. And that can be shared email addresses within a household, shared email addresses or distros within corporations, individuals representing others, so they might have a generic email to cover constituents in their care. Butcher, could you summarize what are the principles applied when behaviors of that type are seen in a feature like email address that would otherwise be in F1?
When you assign a behavior to a feature, that is a general statement about the feature. Like most of the features are, you know, behave that way. You're always going to find exceptions. Like the social security number 1, 2, 3, 4, 5, 6, 7, 8, 9 is not a frequency 1. It's probably a garbage value. And what we do, since we're counting everything, when we find a particular social security number or email address that's not behaving like a frequency 1, we don't say then all email addresses aren't frequency 1s. We say that email address isn't behaving like it's supposed to. And so it loses the fact that it's a frequency few. So the social security number 1, 2, 3, 4, 5, 6, 7, 8, 9, when we find it's been used by 20 people, it's no longer treated like an F1. The same thing would happen with email addresses that aren't behaving like an F1. Now, email address in particular is something that you know, some people might consider the whole, like the email addresses that you guys get, you might want to consider them all frequency fews as a default. And that's certainly your choice. There's also the possibility if if you want to treat some emails like a frequency 1 and some like a frequency few, you can create two different kinds of email features. They won't match across each other, but they'll match each other, and you'll have the behavior that you desire. If you can tell like which of the email addresses are, shared. Okay. Providers will also align their business data phone address somewhat generically. Yeah. And, lots of times you get, more transactional data where, maybe the address on a record coming in is, a company's address versus an individual's address. So that is something that, definitely we deal with. And again, when we get too many people using the address of, say, I often use the example of IBM's corporate address. IBM employs, 300,000 people. If every one of them gave their corporate address, we would quickly make it generic. Now, later on, you're going to see some of those generic thresholds. I'm sorry, the word generic comes about when something starts not behaving like it's supposed to. So the Social Security 1, 2, 3, 4, 5, 6, 7, 8, 9 goes generic. IBM's corporate address goes generic, and it's no longer treated with the same behavior. So I'll leave it at that and see if there's a follow-on question.
Question from the chat, going into the example in table 2 in the principle-based ER doc for multi_FF plus close _name rule, 2 records for a Pat Smith with the same address, phone, and different genders wouldn't match. But in the absence of DOB or other exclusive stable, would it be possible to match or better account for a gender transition? Also, in cases where gender transition occurs, how can we overwrite the previous value without removing records with the old gender value?
Okay. Well, that's a big question. Let me first answer the multiple frequency few and close name. So, a name and an address and a phone is a pretty good match. However, I suppose they could still be, twins or brothers or father-son, something like that. So we would look for things even with that to help break a match. Now, if we do break a match based on a gender alone, then it's still a high strength possible match. I always like to tell people, just because we didn't say it, just because we say we're not comfortable saying it's the same person doesn't mean that we don't have the match. We still have the match. We just refer to it as a possible match. Whenever you get a record, you're going to get a record from the database. You're going to see, if I were to search up a Joe Smith and then get Joe Smith number 1000, I could see what records I assigned to him, and I could see who he's related to at what levels. So he might have 1 or 2 possible matches. He might have 3 relationships, possibly related records. So there is a view to that. I will tell you, in fact, in one of the examples, I do have, that I'm going to show you shortly, I do have a person whose gender difference was overridden with the strength of a frequency 1 as well. So if you had, multiple frequency fews and close name, since there's not an F1, it defaults down to, anything can break the match. If you have an F1, then as well as a name, as well as an address and a phone, then it's gonna override the gender difference. By the way, what I'm going through right now is a series of articles. This is our Zendesk site. And here are so it's Senzing.Zendesk. I can't see it.
It's the Zendesk.com.
Senzing.Zendesk.com. Here's all the white papers we're going through. Here's the EDA Tools Yeah. And so I'm just going to show it to you right here. Here's an example of two George Wiest, a George Wiest and a George W-I-E-S-T. I think I'm just going to go ahead and you know, these two records got on the candidate list. And when we did the scoring, we find that those names score a certain value. We find that the gender scores a certain value. We find that the address score a certain value. The email address, at least on the Y screen, if something is an exact match, we don't show what it matched to in the score. If you're looking at a Y screen, what you see on the left is the value for the record from the column. So customer 1087 is George Wiest with the I. Customer 1088 is George Wiest with an E. So when we do this comparison, we're telling you this George Wiest on this record was matched to, or the best matching value to this record is George Wiest, and it scored 99. And the full name scored 99, the given name scored 100, and the surname scored 98, the difference between the I and the E. So that's an example of, you know, we found two records on the candidates, we do all the scoring, and then we apply principles. So the principle says, do they share an F1 and they have the same name, or very high strength name, and they have a frequency few. In this case, the frequency few is a phone number. Now, it's not an exact phone number. That's why it's CFF, close phone number. They share a stable element, which is the date of birth, right? So that's the same. But there's a different exclusive. So Rule 111, that's a principle. The principle is same F1, name, a frequency few, a stable element, but there is an exclusive difference. Because all of these values are so strong, it's sort of like you ask or you tell the system, hey, if it's got all this strong stuff, what do you want to do if there's a different exclusive? Well, in this case, we said we want to resolve it anyway. And so even though there is this difference, we go ahead and resolve it. Now, name and frequency few would be they share a name and a phone and an address, right? So, you know, that's nice when they do, but it's not that much different than just a name and an address. I mean, it is more different, which is why we have the rule multiple frequency fews. So a name and an address alone might just indicate they've lived there at a certain time together, but a name and an address and a phone is more likely that they really were at that location at the same time. So that's why there are the two different rules. You get to decide for each rule how you want it to behave. I think I'll leave it there for any follow-on questions.
Don't hesitate to send us questions at support@senzing.com about any of the material that you saw covered in this section. Today we covered Senzing's ER process and principles, the details of which influence your data source selection and the features that are required. In the upcoming session 3, we're going to do a live demo of exploring data using a truth set using the EDA Tools.